Hi, everyone. This is a really wonderful crowd. I'm looking forward to interacting with all of you. A little bit of background. So since this is an interdisciplinary audience, I guess I will call myself a card-carrying economist today, but I have quite a bit of, kind of various different experiences. I was an civil environmental engineer as an undergrad, briefly worked as a journalist. I did an interdisciplinary PhD program that was like a mixture of economics and atmospheric science. And then now my primary appointment is in the Bren School, where I have colleagues across all the different fields that kind of study the environment. So I think this is like the way to do, it's kind of like a weird echo. All right, is that? Okay. Like a weird, feels like you're in this weird godlike podium in the background. So anyway, so I think this is the way to do it. It's interdisciplinary work. It's the way I think to do, just to kind of figure out solutions to our environmental problems. It is also not easy, as many of you guys know. And what I'm going to try to present to you today is some of this work that I've been doing using kind of the tools of economics and economic reasoning and economic statistical work, mixed with some insights and also numerical tools and computational tools coming in from the physical sciences. And a lot of my work kind of works in that, operates in that interface. One thing, just to let you know, in case those of you haven't been to an economics seminar, is that we are conditioned to be in very uncivil seminar settings. So I am used to just people asking me questions throughout the talk. I actually think that's good because it shows that you guys are engaging with the material, or you're putting me on my toes, be like, that statement isn't quite right. So you should feel free to just interrupt me at any point. And that for me allows me to get a sense of whether I'm making any sense and whether I'm connecting with you guys as well. Okay, so I'm going to present. Not going to present one paper. In fact, I'm going to present 2.25 papers. This is a bunch of work that is joint with a former PhD student of mine, Donna Hernandez-Cortez, who's a faculty member now at ASU, and a former postdoc of mine, Paige Weber, who's now a faculty member at UNC. And so a lot of this work is work that we've been doing jointly for a few years now, and we'll continue to move forward. Okay. So let's just take a step back. This is something I think a lot of what motivates where I am in my research right now, and I suspect a lot of you as well, is to not just think about how to deal with climate change, but how to deal with climate change in a world that's already very unequal. Okay, and the reason why I spent a lot of time thinking about this is that it is not obvious to me that as we kind of satisfy this imperative to decarbonize our economy, it is not obvious to me that all decarbonization paths are built equal, okay? In other words, to be more specific, it's not at all clear to me that there aren't particular decarbonization paths that won't take a world that's already very unequal and make it even more dispersed, okay? So what are some examples of this, right? You can think about this in basically everything that climate policy touches, okay? We can think about in terms of energy prices, okay? We know as we decarbonize, necessarily energy prices will have to go up, at least in the short run, okay? Who are the biggest, who holds the most burden when it comes to energy prices? It's likely poor households, right? And households from communities of color. Final good prices, this is just economics for saying basically where you're paying, right? We're worried about inflation right now. Inflation is likely to hit the poor households more. How is climate policy going to interact with that? We here in California talk a lot about this term the just transition, okay? The just transition is really short-term, at least as an economist, it's just thinking about wage inequality, okay? And so, for example, if you're talking about decarbonizing the economy, there are still, important pockets of our country and here in California, of our state, that depends on a fossil economy. Okay, they will have to necessarily contract, but what about those workers? Okay, not only what about those workers, but what about that local community for which large portions of their local revenue that goes to schools and hospitals and roads depend on fossil revenue. Okay, we want that to contract, but how do we make up for those losses? Okay, and then the topic of this talk, and I'm happy to like spend a whole afternoon talking about any of these, but what we're going to talk about in particular is about local air pollution. Okay, climate change, right? As an economist, we consider like greenhouse gases as a global externality. It has differential spatial impacts, but locally, okay, it's like a ton emitted of GHG anywhere is basically the same. Local pollution, not the same, right? We're here worried about the fact that carbon dioxide is often co-produced with particulates, toxins, NOx, SOx, which we know, as I'll talk about, have differential exposure between rich and poor. And so the question here that we're going to think about broadly is, how do we think about decarbonization policies that hopefully would not widen existing inequities, but could actually be an opportunity for us to narrow those inequities. And in particular, what we're going to focus on for the next hour or so is to think about pollution disparities, air pollution disparities, focusing on like particulate disparities. Okay, so that's the broader context. Are there any questions? Okay, so why is this an issue? So here are two graphs that outline something that I think many of you guys have seen different versions of, which is that it is very well documented here in the US at least, and certainly here in California, that communities of color, low-income communities are exposed to more pollution hazards. Okay, so this is the kind of, you can think of it as like the underlying, impetus for a lot of concerns that we broadly call environmental justice. So environmental justice is broader than just about air pollution. Okay, so just to give you a sense, these are just two figures from the economics literature. You can find different kind of figures across all the literatures that you guys operate in. But this is showing, for example, in the state of North Carolina, where facilities that emit toxic releases are located, right? Those are showing you in these dots, okay? And then also shaded, by zip code, the median income, right? So poor households are exposed to more, or at least located, specifically located to more facilities that release large toxins. At a population level, this is work by economists Janet Curry, John Voorhees, and Reed Walker, showing that if you were to just look at like the spatial distribution of pollution across the US, particulates, ambient pollution, basically, and you can just kind of spatially weight by where white individuals live and where Black individuals live in the cross section like today. Basically, you see a fairly kind of relatively even distribution, okay, for white individuals. If anything, like the more polluted places have fewer white people. But for sure, you see a very clear gradient, right, where the most polluted people locations are also where Black people live. Okay, so these are established gaps, pollution disparity gaps that we worry about. Okay, but we also want to think about policy interventions that help address this. Okay, and so that is in part what I'm going to discuss in the papers that I will present. So the broader question is, as we think about decarbonization, as we start decarbonizing our economies, which we are doing here in the US, what would happen to local air pollution disparities? Okay, as we start talking about here in California, all these policies to go net zero, what will, it's likely that air quality will get better because these pollutants are co-produced with GHGs. But what happens to that gap between advantaged and disadvantaged communities, okay? Between minority communities and other communities? Will this gap narrow or will it widen? Okay. I want to argue that it is not at all obvious. Okay. Why? Several reasons. One is it has to do with how GHGs and local pollutants like toxins and air pollution are co-produced. Okay. Second, we just think through this, it actually turns out to be very complicated because it's about the joint spatial distribution of where pollutant facilities are, how do they react to different policies, and where households live, households of different demographics live. You can actually even layer this even more, which is if you start thinking about like where people move, okay, potentially, it actually becomes even a harder question because think about this story. A place cleans up, but gentrification occurs. Housing prices get higher in that place. Okay, poor households and households from communities of color tend to rent and not own their homes, and so now are forced to have to move to somewhere else and not be able to experience the cleaner air. Okay, I'm not going to talk about this, but for all these reasons, it is not at all obvious that like our standard tools of just like let's go in and clean up a place necessarily narrows the gap that we're seeing in terms of what people are actually experiencing. Okay. Okay, so that's a lot, but let me just focus on like two particular challenges in a more narrow sense that I'm going to deal with in these papers. Okay, first is, can we just simply say like if we're like interested in a policy or something that's happening, you know, to the energy sector or electricity sector, can we just like simply just probably just simply estimate changes in the spatial distribution of emissions due to policies? Okay, so here I'm going to bring in some tools from like econometrics with like a causal inference flavor. So we're going to think about treatment and control to actually estimate what happened to pollution when policy was reduced relative to the absence of that policy. The second thing, and this is where it's less about economics or econometrics and more about like modeling the physical science, is how do you actually, when you like say like, oh, a power plant is going to get cleaner, okay, how do you convert changes in emissions from that point source onto the spatial distribution of pollution concentrations that people are actually breathing in, okay? And here we're going to have to basically couple econometric techniques with pollution dispersal models. Okay, and a lot of my work is trying to figure out how to do that coupling within like a unified statistical framework. Okay, any questions? So I'm gonna have until 11:50, is that right? More or less.
Yeah.
Okay. You can please just ask a question along the way. Okay, so here are two contests. Okay, the first paper I'm going to focus is just on California. Okay, and the other is, and it's a retrospective study looking backward. The second one is going to be US wide. Okay, in California I'm going to focus on industrial sources of pollution, and even in the US I'm going to focus on the electricity sectors. This is what I plotted here is for California and overall for the US. So the x-axis is time, okay, and the red line is GHG emissions overall for California and the US. I just want to take a pause here because like these two graphs are actually incredible, okay? Because also in the background here is GDP per capita during the same period, okay? The reason why, from my standpoint, this is incredible is because there are actually no examples, very few examples in modern industrial history where we've actually seen what economists would call decoupling, or you guys would call it decoupling. That's what decoupling between GDP per capita and greenhouse gas emissions. Okay, so like what you don't want, is the COVID example from the last 2 years, right? Like we know like greenhouse gas emissions fell. But like none of us will be like, oh yeah, this is the way we want to engage in climate policy, right? Like just doing that 10 times more. Like that's not smart strategy. Okay, what you want is a rough world where like your emissions are declining and you're maintaining a certain amount of economic activity and improving economic activity. Now, of course, GDP per capita is not the statistic we should all rest our laurels on, right? It also masks a lot of inequities, and we'll talk about that. But in a kind of like a high level view, this is actually pretty incredible. Like when I started working on this in the early 2000s, if you told me that like both of this was going to happen, especially in the US, I would be like, yeah, I'll take that. It seems pretty good, that we would actually have declining levels of GHG emissions while increasing, without destroying our economy. Okay, so we're going to study. This is why we can do this retroactively instead of doing simulations in the future, because we can actually study what's happened in these two contexts in terms of local air pollution disparities. Right, because we are actually on a decarbonization path right now, both in California and broader in the US. Probably not fast enough, but we're on that path. Okay, so this is not in some sense like an abstract setting. Okay, all right. So the first paper, we're going to try to think about now the first challenge, like how do you actually isolate emissions changes? We're going to use a causal inverse framework. What is that? Just really very simply just thinking carefully about treatment and control and confounders. okay? And we're going to focus in particular on California's carbon market, the greenhouse gas cap and trade market, which remains today the world's second largest carbon market, and it's been in place since 2013. The second paper where we're going to think broadly about the US, we're going to think about the big thing that's been happening in the US in the electricity sector. Why, by the way, like this decline in US emissions, it's all, you guys probably know this, like as energy graduate students, like this is all electricity. Like if you look at every other source of GHGs in the US, it's just like flat, maybe increasing a little bit. So this is all electricity, but we don't really, I would argue, we don't really exactly know why. Is it renewables? Is it cheap natural gas? Okay, and in particular, during this period, there has been, and continues to be, a lot of coal to natural gas fuel switching. Okay, not here in California because we like never really use coal, but for much of the rest of the U.S., especially in the Midwest and the South, in the Southeast, where there was and still to this day like coal generation. This is, we think, some fuel switching is going on. So we're curious, this fuel switching that's been going on, how has that altered pollution disparities? Okay, across the US. Okay, and there I'm not going to be able to do a causal inference framework because that's like a national experience, right? So like when a whole country experiences something, you're like, you have no control group. Okay, and so the best thing we can do is just like make some statistical assumptions and just do like a decomposition exercise. Okay. All right. The second challenge is, let's say like we solve the first challenge of like figuring out what happens to emissions. Okay. We don't actually, at the end of the day, care, I would say, about emissions. We care about what people are actually breathing in. So I would say like there's a distinction. The distinction I use in terms of technology is like emissions versus concentrations. In fact, concentrations is not really what you want. What you really want is like exposure, which is like, you know, like concentration is like what's the PM outside. Exposure is like I'm here inside right now, right? What am I actually breathing in? And then I'm going to show you again, actually, you don't really care about exposures. What you really care about is actually health outcomes. Okay, it's like pollution in its own. Largely, it's like because we worry about health outcomes. But I'll get to that in a second. But let me just say, let's just start with the first problem, which is like you have emissions. What happens to air quality? Okay, so this is actually like maybe I hope none of you guys do this, or maybe some of you do this, but like at least economists and social scientists have been doing this for decades, which is like, all right, it's like this is like a zip code. Okay, this is a power plant. Okay, where's the air quality change? One thing is like, it's just like in that zip code or in that county. It's almost like assuming that like, you know, like the dirty air like gets to like a zip code boundary. You're like, not going past here. Okay. Obviously that's silly. And then like a little bit more sophisticated version is like, let's just have a ring, right? Let's put like a ring around the pollution, which is like a little better than this. But that also has some assumptions about spatial distribution, right? It basically says that like pollution moves uniformly, right, within that circle. Maybe there's a kernel in which like it decays, but at some point it has the same like let's respect the boundaries that the researcher imposed. Okay. Okay. So what we're going to try to do is actually leverage a lot of like recent advances in high spatial resolution pollution dispersal. Okay, in the first paper, we're going to use a product that many of you guys have used called HiSplit. It's a Lagrangian particle transport model. Just think of it as basically like you have a bunch of like Navier-Stokes equations that tell you like how particles will move, right? In space and time, like driven by like pressure gradients and temperature gradients, and you just like drop like a particle, and it shoots the particle, right? Following those gradients. Okay, that's great. There are limitations to that. We also use another version. The main limitation to this is that it doesn't model like chemical interactions. Okay, so like the atmospheric chemists in the room will be like, we don't like this because like it disrespects our entire field. So we also use this other product called InMap, which some of you guys have heard. So like running a full like atmospheric chemistry model at most like spatial resolutions we care about, like a WRF-Chem model, would take like a year to calibrate. Okay, and so there's been a team of scientists led by Chris Tessum at Minnesota, where they basically like linearize this relationship, right? We all know the world's much better when it's linearized because then you just like apply a matrix, right? And then it's just like a bunch of sums, and I'm just going to show you like a bunch of sums. But it can create with those kind of that reduced complexity matter plumes okay, for any pollutant that you shoot up, for any source, okay, all you have to do is just like put in like lat, long, how much, and it's all linear, so you just put in like a particular like pulse, and then you multiply that pulse by the actual quantity of the emissions that you observe, okay? And so what first paper uses this, actually uses both. A lot of our more recent work is actually using this, okay? And there are actually limitations to this as well, but we can talk about it. Okay. All right, so basically what we're going to do in both papers is to like take our like econometric techniques to isolate policy-driven, right, or policy-driven emissions, or emissions that are driven by a particular cause, and then feed that into these pollution transport models. I'm going to use the word couple loosely. This actually is not right. Couple is not right because there's no like reverse feedback, but it's integrated in the sense that we're going to try to think about like statistical uncertainty jointly with both the statistical uncertainty as well as like the model uncertainty. Okay. Yeah.
For a little bit of clarification, is the model on the right using pulse functions, or is it like a transient analysis of emissions?
What do you mean by transient?
Would it be like over time, this power plant's emitting this amount of SOx and NOx, and then you model that over, let's say, like a year, or is it a one and done? Where does all this pollution go?
So the model itself is the latter, so one and done. You can say like it is basically what we call like a source receptor matrix. Okay, you give it a pulse, it tells you, right, from that X, Y, Z, right, as well as some other characteristics like the temperature and speed comes out of the smokestack, where it goes. Now you can do the former by basically saying now like I have some long-term change in pollution, right, that I will feed into the model, and you can handle that, and you can handle that because it's all linear. So it's just, I'll just show you like it doesn't because everything just ends up being a bunch of sums. Okay, that's the kind of how it takes this like really hard computational problem and just like linearizes it. Yeah.
How are you determining?
Okay, so I will tell you that's the first part. That's like the emissions part, like isolating the drivers of emissions. Yeah. Yeah. Good. How many people have used either of these products? Yeah. Which ones have you used? In that, yeah. It's so Chris has like developed like a very nice R/ I think R Python package to run this. So I mean, the problem is that like it's getting so popular that like the server crashes all the time. But it is like it solves a lot of problems. But there are also limitations to this. In fact, Chris Sessom, Paige Weber, Donna, and I are writing like a review paper of like how do you use InMap for social science research. So, maybe like a year down the line. Okay. Okay. Before I go into details of the first one, are there any other questions? You guys with me so far? Okay. All right. So the first paper, we're going to think about California's carbon market and what it did to pollution disparities. The backdrop is the following. So, at least as an environmental economist, I have we as environmental economists are very excited about market-based environmental policies, maybe a little bit too much so. Why? It's largely because we think of pollution as fundamentally a missing incentives problem. Okay, why? It's like we go out and pollute. The reason why we pollute too much is because we don't bear the consequences of our pollution. That's like a classic story of externality, right? I go out and I don't know, drive a gas-powered car. I think about the cost of gasoline, but I don't think about the damage that that's doing to everyone else through local pollution and damages to the climate because it's not priced in. Okay, and so from that starting point, you're like, oh, well then the solution is just to price the thing. Okay, and so that's basically market-based policies, and we have a bunch of theoretical properties about them that we've had for 50 years that make them very appealing. The central theoretical prediction is that for any given overall target, right? Say California's 2030 carbon target, which is 40%, I think now below 1990 levels, right? There are many ways to do it. There are an infinite number of ways to reach that target. But in theory, the cheapest way to do it is through our carbon price. carbon price basically incentivizes abatement in the order of cheapest to most expensive, right? You could achieve like California's carbon target by like saying like, oh, we're just gonna do fusion. And we're like, oh, we're still like 20 years away from fusion, okay? So that would be like one extreme where it's like super expensive, or you can be like, we'll do it all through carbon capture and storage. And you're like, well, carbon capture and storage right now is like $300 per ton, okay? So there's a glide path to achieving that given existing technologies that is least cost, right? And you start off basically like from the cheapest all the way to the most expensive. Now, what's hard about that is that we don't observe, at least I would argue, we don't observe what that marginal, what every option's marginal costs are. So there's like almost like an informational barrier. It's like in theory, if I knew every abatement option in the economy, and I knew exactly how much it would cost, I could just be like a dictator and be like, all right, first you, like farmers, then you, trees, then you, electricity grid, and like march up. We don't have that information and we don't have that dictator, okay? And so therefore, a carbon market can step in and achieve that in theory, okay? By just basically setting a common price. And so those with the lowest of marginal abatement costs will do more abatement, right? Because they know their own private information, okay? And those, and like the fusion guys will be like, yeah, I'm not gonna do anything because like my abatement cost is like in the tens of thousands, okay? All right, so that's the appeal, okay? And it has kind of led to a lot of adoption in fisheries. My colleague Chris Costello, who's done a lot of work with this, quantified that about 30% of global fisheries have some kind of market-based incentive system. My other colleague Jim Salzman at Bread documented there's about $36 billion in ecosystem payment services. So these are all like different environmental domains. And then in greenhouse gases, about 20% currently of greenhouse gases under carbon market, and this could double under Paris. Again, the key force is that you introduce a market, that market then uses like incentives to figure out how much abatement goes on. So it spatially reallocates where emissions come from. But this spatial reallocation is itself the core EJ concern. That is, if you spatially reallocate pollution, it is possible that you end up with different abatement that differentially affects disadvantaged communities more so than advantaged communities. In fact, the market is agnostic about this, okay? And so this central tension is that the same market forces enabling cost effectiveness, right? Allowing us to achieve something at least cost could actually be exacerbating our pollution disparities, okay? So we're gonna study this, and this has been, for those of you who follow this, it's been like extremely controversial in California. In fact, these concerns have been there from the very beginning, and they like continue to be concerns going on. So in California, we started off in the 2000s with AB 32, which set the cap, right? That at the time, it was setting the cap for 2020. It's since been extended by SB 32 to 2030. Establishes the carbon market, which is now the world's second largest after the one in the EU. And he had this particular eligibility criteria that said, point polluters, industrial, of all kinds of major polluters, basically, if you're above a historical threshold, 25,000, okay, you had to participate in this carbon trade market. You had to face the carbon price. Below, you didn't. Okay, and we're going to use this threshold basically for assigning treatment control. So we're going to compare facilities across this threshold. We're going to think about a definition of disadvantaged communities. Well, this is actually kind of tricky. Like, I feel like if I were to ask any people in this room, like, how do you define a disadvantaged community? I don't think we would have a consensus on what that definition is. In fact, I don't think we, in general, know and like can say like this is a disadvantaged community, this is not a disadvantaged community. So we wrestled with this issue for a while, and so rather than like come up with our own definition, we're just like we're just going to appeal to the state. The state has a definition. Some of you guys have seen this. It's called a cow and it's based on this cow and viral screen score. Okay, which basically like it's like a it's like a cross product of like a bunch of exposure measures and demographic measures, and then they rank, they come up with some arbitrary ranking and arbitrary threshold, and so above this threshold, you're disadvantaged. Below this threshold, you're not, okay? Not like perfect, but we also like, not like we were to undergo the exercise, we'll come up with something just as imperfect. So we just went with what the state does. So we're gonna basically ask, If you're treated versus control, what happens to your pollution emissions relative to control facilities after the introduction of the cap and trade program compared to before? So for those of you who've done something like econometrics, it's like a kind of a difference in difference framework. And then we're going to take the predicted emissions and feed it into a pollution transport model to see where that emissions goes. And then we're going to look at how the gap between disadvantaged and other communities change after the program. Yes.
I have a really strange question. So with the hard sort of 25 kilotons of CO2 per year, has there been any evidence of like, I don't know, someone saying I'm emitting 24 kilotons, I'm not gonna expand my facility, I'm gonna make a new facility? Like, has there been any tomfoolery with that?
Yeah. So there are two versions of your tomfoolery question. The first is, was there any tomfoolery that went into the definition of that? Right? Meaning like there were lobbying that went on and said like that got certain facilities out of it. And then there's the question of, once that was established, was there facilities trying to like move around that after the program? Okay. So the first form of tomfoolery, we don't think is as likely because it was based on historic emissions before the policy even was proposed. So like, it was like, okay, the policy was proposed, I think like some early drafts they were proposed in 2009, and the emissions were based on like earlier definitions. So there's like a sequencing of it, of the timing that I think we hope gets us around that problem. They can't go back in time and change the numbers.
Yeah.
The second form, yeah, that for sure could go on, and you can interpret any effect of cap and trade as inclusive of that, you know, whatever behavior around the threshold that would occur. Yeah. And so, so you can say that like, you know, maybe, you know, whatever we're seeing is like inclusive of the cap and trade effect is, you know, including that behavior. How that behavior exactly plays out is hard for me to think through.
Interesting. I was just confused about that sort of hard boundary.
Yeah. Yes. Yeah. I mean, this is pretty common. Like, in a lot of programs, this is pretty common. In part because they're like monitoring costs.
Yeah.
Like it's like if you have like a really small facility, like you have like a diesel generator, right? Like you're not just part of monitor and yeah.
Thanks.
Yeah.
So when you talk about doing a market for cost effectiveness, like, are we considering people's health impacts, or like, you know, what if we damage the environment for future generations? Like, does this open the door for corporate lobbying? Like, you know, the American Petroleum Institute knew about climate change back in 1980, but before, you know, any of these targets were set.
Yeah, so it's a good question. So it may come as a surprise that actually a lot of our policies are designed without benefits per se explicitly considered, and here's why. Okay, so from an economic standpoint, the way we would think about it is to say, if you're going to introduce a policy, reduce pollution, right? You want to balance the cost of doing it and the benefits of doing it. Okay, so the benefits would include the items that you mentioned, as well as all other kind of benefits that come with it. Okay, and you know, you would, at least from like a marginalist perspective, is like you want to set the pollution at a level that where marginal cost is much better. Okay. In practice, what often happens is not that calculus. In practice, what happens is there's some political process that says we're going to achieve X. X being in this case, AB 32 saying emissions will fall by 20% relative to 1990 levels by 2020. Okay, how do we get there? And in fact, that's what we're doing in California. Like we're saying, like now out of 2030 and 2040, we have this like carbon neutrality target. It says we're going to do this. Okay, how do we get there? Okay, obviously the reason for that is thinking about all the benefits of doing it, but the actual quantification of those benefits doesn't go into the calculation. Okay, the reason why, I mean, there are many reasons. There are political reasons, there could be economic reasons. Like the benefit of environmental improvements are one very hard to quantify. There's like a whole field, or at least there are a lot of environmental economists and certainly environmental economists, but also other fields of thinking about valuation, very hard to quantify. Another is that for political reasons, like it's just, I think in general it's been like much more attractive to like have people focus on a target to say like, we're gonna do this by 2020, okay? And so in that sense, if you have a target, then the question that we're left with is how do you achieve that target in a way that is least costly? Yeah, and that's how we often think about these policies. Like, so you have the 2020 target, you have this 2030 target, this 2050 target. How do you do it in a way that's least costly to the economy? And I think where a lot of us are moving to also is just not just thinking about total cost, but how do we achieve it in a way that also doesn't exacerbate inequities?
But doesn't this mean that, because when you decarbonize, there's all these different actions that need to be taken, we don't have perfect data, we're not being perfect at anything we do. But doesn't this mean if we say we're only considering quantifiable factors, that a certain number of things are always going to be ignored? And if you consider, if we're not sure, are we going to sway this thing towards being more precautionary, which is I think what a lot of environmental justice movements want, like okay, we don't know the exact cost of running that fossil fuel plant, but it's probably bad for us. Let's assume it's bad, versus saying we want to maximize our market potential, we want to maximize GDP, we're going to downplay, social pollution to an extent. Can that significantly sway the outcomes, and especially like who has what value on the system?
Yeah, no, these are really good points. I mean, let me try to unpack it a little bit. I think there's the issue of quantification, and there's the question of what do you do with it. At least that's how I think of it. One of the major challenges in my interactions with EJ groups is actually for the things they argue are central concerns for their community. There's very little quantification. So we know, for example, that if you look at like EPA pollution monitors in the state or anywhere, like they're not in low income places. And so like one of the things that like has been a central part of EJ group advocacy and recent bills is actually having funding exactly to quantify better air quality in low income communities and communities of color. So it's not that it's not that like there is my sense, an allergy for quantification. In fact, my sense is like there's a desire to say we want to actually know better what's happening. Your second point is, I think, equally valid, which is like, well, what are the numbers? Is it being taken seriously, right? And that I think is another thing that I think is I know less about. You would think of it sometimes as like falling into this issue of like procedural justice. It's like, broadly speaking, like if you look about environmental justice or just justice concerns, there's like distributive justice and procedural justice, right? Distributive justice is kind of like, we have good numbers, what are the numbers telling us in terms of what we're facing? Procedural justice is more like, do we have a seat at the table to then like have a voice to fight back in a way that isn't that it's on par with other groups that have historically been more advantaged. And I agree that like that's something that is oftentimes missing, but in my mind is separate from the measurement issue. Like the first one is like having good measurement in these communities is powerful and could be useful. But the next question is like once you have it, are you still going to improve? All right, so what we're going to try to ask in this paper is that, okay, so think about it this way. We want to think about what the carbon market did to pollution disparities. The way to think about it, at least from my standpoint, is like, from a causal inference standpoint, is like, suppose you have a gap in pollution disparities, right? Disadvantaged communities breathing in dirtier air, okay? The causal question is that when you introduce a carbon trade market, did it widen? Okay, sorry, this is like, so did it widen or did it narrow? Okay. And so you can think about this as trying to quantify what, so that to me is like, you need to think about the time dimension of it, all right? And I just want to highlight that actually, like from economic theory, it's ambiguous. So what does an environmental market do? It induces more abatement, okay, from lower cost polluters. It's like less abatement polluters with like steeper marginal abatement costs. And so then it's all about the spatial relationship between whether or not those facilities are upwind of disadvantaged communities. If like polluters with steeper marginal abatement costs are upwind of disadvantaged communities, the gap will widen, okay, because of this reallocation driven by the market. However, if the opposite relationship is the case, it could actually narrow, okay? So it could go either way. And so part of the kind of research question here is like what actually happened, right? And I also just want to mention, like, it's actually very hard to predict this ex ante. Going back to this whole point of like, it's almost like epistemic, like we don't observe marginal abatement costs. If we did, we could actually like say like, oh yeah, like facilities with high and low marginal abatement costs are located relative to poor income communities. We can run a simulation, we could know basically what a market would do. But we're missing the ability to observe marginal abatement costs, okay? Or rather, you also don't trust what polluters would tell you. You're to ask like, what is your cost of abatement, right? Then you actually have to do these like, you know, retrospective studies because the outcomes reveal in some sense what's going on. Okay, so we use data that's actually pretty standard. Any of you guys can access this. This is, you know, in California we have panel data, so facility by year data on emissions for carbon dioxide or, you know, CO2 equivalents, particulates, 2, 5, 10, NOx, and SOx. Have it every year. We know their regulation status, regulated or unregulated. We know, importantly for our work with the pollution transport model, their location, their sector, their stack heights. We're going to actually, for our analysis, so this is going to be important, we're going to restrict attention, we're going to remove refineries and electric generators. The reason why is that those facilities, for those of you who follow California policy, are regulated with other things. We have the renewable flow standard for electricity, and we have the low carbon fuel standard. I'm here at ITS, like we have the low carbon fuel standard for refiners. Okay. The reason why it gets complicated is that when you have these facilities that are regulated by multiple policies, you don't know which policy is binding, or we'll call it binding. And so when you include them in your estimation, you don't know whatever you see is due to just cap and trade or the RPS or the renewable portfolio standard. And so as a result, you actually don't know how to interpret it. And so what we're going to do is we're going to not look at it. It does mean that our estimating sample is a much smaller share of California-wide emissions. But in some sense, like the only set of facilities for which we can say anything causal about a carbon market is a much smaller set of the total set of regulated facilities. Yeah.
Can you include interaction terms for all three to then see if there's a binding effect? So you could introduce a dummy variable for CNT, then one for RPS and one for LCFS, and then an interaction term multiplying all three. And if one or the other binds, then that coefficient for the interaction term would tell you what the effect is.
Yes, you could do that. The problem is interpreting that interaction term is not so straightforward. Because when you interact that, so suppose I did what you would suggest. Do I interpret that interaction term as being the effect of CRBS? Or is it the effect of the differential effect of an electricity generator?
So I'd start with both, so CNT multiplied by RPS, RPS multiplied by LCFS, and all the combinations, and see at least in conjoined impact of the two.
Yeah, and I'm just saying like electricity generators are all regulated by the RPS, or they all fall subject to the RPS. And so if I see a differential effect, is it because electricity has a different effect? Or is it because this is electricity's effect plus the RPS?
It would be a bit of both. So I think the interaction term coefficient and
yeah, no, so I think we're saying the same thing. It's just that then I don't know how to interpret that.
Wouldn't the coefficient tell you that? At least with the limitation of the econometrics.
I mean, a coefficient is a coefficient, right? It's always a number. The question is the interpretation of that.
Yes, so for the interaction term, how much would, let's say, CNT and an RPS together impact the environmental justice outcome variable? And you control for other things, like you said, if it's for the electricity generation in general. So maybe carbon intensity of electricity generation, did that person. So control that as well, if you're including the interaction term, control for whatever other confounders that may follow it, if you include that with the model. And then any bias that might be in the interaction term coefficient will be countered because you're controlling for things. Of course, not perfectly, but still somewhat.
We can talk about this later. I mean, I think I hear what you're saying. The issue, in my mind at least, is that you don't have all facilities, all electricity facilities are regulated in the RPS. So it could so then if they have a different response, how do you know that interaction term is due to it being electricity or it being under the RPS? And we can talk about like how useful that would be under this ambiguous interpretation. Maybe that's where we can go. Okay. So just very quickly, so basically what we have is here's a map of California, this is your state. Darker areas are areas that Cal virus groups score cause disadvantage. Lighter blue areas are those they're not disadvantaged. I'm not going to contend with this definition. I'm just going to take it as given. Here are all the regulated facilities in black dots. Basically, we're going to estimate a statistical model, which I'll show you the results from. And we're going to then take predicted emissions driven by the policy, feed it into high split, this Lagrange particle pollution model, which will generate basically, you can see like basically spaghetti plots or like plumes of where the pollution is going. We're going to collapse this to the zip code level, and then just look by disadvantage and disadvantage zip codes on average whether the pre-existing gap, right, changed, whether it widen or narrow as a consequence of the policy. Okay. Just very quickly, just some of you, this might be obvious, like why do we do this like treatment control idea? It's just basically if you just look at regulated facilities, which other studies have done, the problem is that like there's like a zillion things that determine emissions, right? So like during this whole period, there's also like the drop in natural gas prices, okay, and other macroeconomic changes to the state. And so if you just look at regulated facilities and look at their emissions trends, you don't know if that is due to cap and trade versus these other forces, right? And so you cannot claim that this is the consequence or the pollution disparity consequence of the cap and trade market, okay? And so having a control group, right, removes some of that. And so you're estimating differential emissions for the treated facilities relative to control facilities before and after the policy, okay? All right, so here's the paper, which you can find on the website, has a lot more details, but here's the headline result. This is estimating, just to tell you, the differential emissions between regulated and unregulated facilities before the introduction of cap and trade and after the introduction of cap and trade, okay? So one thing we see that's very striking is that there is this like this trend, that is that emissions for regulated facilities were growing faster compared to unregulated facilities. This is not too surprising because they're bigger, okay? Right? This is part of the design of the program. We can't do anything about that. What we see is quite striking, at least in terms of CO2 emissions, is that after this policy was introduced post 2012, the regulated facilities had this trend break, okay? That like it falls relative to unregulated facilities. Okay, so this fall in like CO2 emissions is actually quite large, about 9% per year. Okay, this is CO2 equivalent. We see the same thing for PM 2.5. We see the same thing for PM 10. We see the same thing for NOx, and then we see the same thing for SOx. So these coefficients are much noisier. SOx data is just like for reasons that I'm not clear on. Okay, so we now feed this into high split. Okay, and this, for those of you who run this high split, like this is why we moved to InMap. It's like super computationally intensive. We actually run like 2 million trajectories with like our our regulated sample facilities. I wouldn't recommend going down this path again. It takes about like a week on a high performance cluster. This is why we're like moving everything to InMap now, where everything is linear and you have a matrix. But this is like a few years ago, and InMap was not there. So we did this. And you can then take these predicted emissions and then collapse it to the zip code level. So it's just showing you like the average, okay, over a sample period from 2008 to 2017 of like, this is now policy-driven pollution exposure. This is not ambient pollution exposure. This is the thing that's policy-driven, okay? And we can do the same trend break model. Now, instead of comparing like regulated and unregulated facilities, we're looking at, you know, disadvantaged zip codes versus other zip codes. Okay, we're looking at that gap. So for PM, what we see is, you know, same thing. It's like, so this is, notice this number is positive. So we know we have pollution disparities here in California. Okay, this was growing. It was getting worse in the period leading up to the policy. And the thing that was really striking is that we see a trend break here as well. Okay, that this disparity like starts falling after the introduction of the policy to the point where like it's 5 years later is roughly back to where it was 5 years ago. Still there, not eliminated. Okay, but it looks like the policy at least has narrowed disparities. Okay, as a consequence. So this is for PM 2.5. This is now like going through the pollution disparity model. This is PM10, same thing. This is NOx, same thing. SOx, very big confidence interval because the emissions effects have very big confidence. Thanks. Okay, so it looks like for these pollutants, what we're seeing is that the policy, at least for sample facilities, has indeed narrowed pollution disparities. I'm going to show you something at the end, which you're like, oh, this is great. But I'm going to show you something at the end that's going to like give you pause about whether this is like itself necessary. Okay, and I'll return to this later. Okay, in the paper we do a whole bunch of robustness checks looking at like different assumptions both in our statistical model and how we use high split and then how we like collapse everything. I don't have time to go into it here, but basically you can see like this is our main estimate. These are like point estimates. Main estimate 95% confidence interval, and then point estimates across like over a dozen robustness checks. And so at least the checks that we at least conducted, it looks like this is a pretty stable result. Okay, and then one thing where it falls apart. You remember my earlier slide of like, why do you use like, you know, pollution assignment to like a zip code or rank? Turns out if you do that, you get results all over the map. Like here's what you do if you just say like pollution stops at that zip code or the facility is in. What happens if it stops at like what is 1.6 kilometers, like 1 mile? 1 mile. I don't know why we're doing this in kilometers. 2.5 miles, 6 miles. And you can see that like we get results all over the map. So like this for us was like, you know, like doing this properly, like actually modeling where pollution goes was really important for getting this result. Okay, any questions about this?
Can you get into the review of the model itself? So how did you specify the outcome variable, treatment, and the controls? So the equation that you put in, if you have it.
Yeah. It's funny, if I were giving an income talk, I would spend like 20 minutes on that equation. It's a two-way fixed effects model. So facility, near fixed effects. Outcome variable is transformed, which is a lot of zeros. So it does an inverse hyperbolic transform. It's similar to like a log transform, except it keeps its zero values. And then we estimate a trend break model. So we basically think of a dip and dip model, like treatment, like post interacted with treat. But the difference in the trend break model is that instead of basically seeing if there's a difference in means, you're saying is there a difference in trends and whether that trend broke. And then the model has standard errors which clustered at the county level to allow arbitrary forms of spatial correlation for zip codes within the county and arbitrary zero correlation for zip codes.
And these are robust standard errors because it can be.
They're very robust. They're clustered.
Okay.
So it has both it respects heteroscedasticity within the county and then also allows for spatial correlation for arbitrary form and zero correlation. Okay. All right. Let's take the second paper also with Donna and now with Paige. We're thinking about this question across the US and specifically to the electricity sector. The motivating factor is the following. Many of you guys have seen variants of this. Like those of you who study US electricity know that like there's been like pretty major transformations in the last 2 decades in the US electricity sector. So on the left here, starting in 2000, I'm plotting emissions intensity for NOx and SO2. So you can just think of it as like emissions per kilowatt hour, okay? And I'm showing it to you for cold
EGUs, generating units, natural gas generating units, and oil generating. Okay. The thing that's really striking is that if you look at both NOx and SO2, for coal EGUs, this is falling dramatically. Like coal-fired power plants have gotten much cleaner in the last 2 decades. A lot of it, at least from the economics literature, I think has to do with enactments of like various different variants of Clean Air Act. Okay, over the last 2 decades. The other thing that many of you guys know is that there's been massive switching. So this is like within a coal generator, right? It's gotten cleaner on average. But we also know that there's been massive amount of coal retirements, okay, and new natural gas facilities, right? So the crossing point, so coal used to be in the start of the century, 80% of U.S. electricity, okay, and at the end of our sample in 2017, it fell to about 50%. Okay, and now we're at a point where this has continued. There's more natural gas than coal. Okay. So what we want to ask is how did these phenomena contribute to air pollution disparities? Okay. First, we're going to see like in overall what's happened to air pollution disparities from electricity. So this is why we have the bring in the pollution dispersal model, right? So you can look at ambient measures and be like, oh, like ambient measures have changed it. But if you want to say something about what's happening from electricity, you have to do the source attribution. Okay. And so to do that, you have to run the transport model, okay, forwards. Okay. So we're going to try to do that by using pretty standard data. So we're going to use across the U.S. There's there's SEMS data, continuous emissions monitoring data. Right. So this is data like at major power plants. You can track emissions coming out. That's been around for about 2 decades. Covers all EGUs, electricity generating units, fossil generating units, about 25 megawatt hour. You get hourly generation as well, fuel inputs as well as NOx and SOx. We're going to have a bunch of like things about like characteristics like stack height and so forth that's going to allow us to feed into InMap. And then we're going to have a bunch of census tract demographics for us to say something about what's happened across different communities. Okay. We're going to use InMap. Again, the benefit of InMap here is that the previous high split doesn't allow for atmospheric chemistry. Okay, and we know that like not only do particles interact being important, but actually what happens often is it's important. It's like secondary pollution, right? So it's not like NOx per se we worry about, but how NOx decomposes in the atmosphere with particulates. And then actually we also worry about how NOx contributes to ozone. So this can do that in very fine scale. Limitations, the biggest limitation is that they've only like linearized an InMap run for the US for 1 year, 2008. Okay, so whereas with high split, what high split does is like it basically feed in, right, like NOAA real-time atmospheric conditions, right, that you then run, right, using the atmospheric conditions of that time. This is basically saying they've calibrated it to transport patterns from 2008. This was like someone's whole PhD, Chris's whole PhD. And now, like, we're gonna just, when we like look at data elsewhere, we're gonna just assume patterns in 2008 are consistent over time. Okay, so that's one of several limitations. Okay, so we cannot do the treatment and control kind of statistical framework here. Why? Because like everyone is treated. Okay, there's no control group. Okay, these phenomena, like there's no control group, and so what we're going to try to do in terms of understanding like determinants, I'm not going to call it causes, I'm just call it like determinants, is to just do like we're going to represent it in a very basic decomposition. Okay, this is many fields do this, right? In like high school chemistry, we're probably like it's the term has been dimensional analysis. It's like you take something, you multiply and divide by something, and then like eventually everything cancels out, and all right. Like like sometimes like in like macro economy things, they do like an IPAT decomposition, which is like something similar. So we're going to do the same thing here. We're going to have like emissions equals emissions per output, okay, times right out for that EGU. So sorry, facility J in year P for pollutant. In year T for pollutant P. So this is emissions. This is like NOx per kilowatt hour multiplied by kilowatt hour for that EGU over all the EGUs in your economy, so that's the share, right? And then QT, cap QT is just total EGU, okay? So everything cancels out, right? You know, of course, the validity of this approach is based on two assumptions. One, these three variables do not co-vary with each other, right? They're independent. And this is like the right decomposition, right? So like, sometimes like, when you think about this hard enough, you're like, I could have written this anyway. It would have been like emissions for number of frogs for number of chairs, total chairs in the economy. Like you could, yeah, so it has to appeal to some logic, but at the same time, it's like, you could have made anything up. But just, you know, we're gonna do this. This is gonna give us emissions. We're gonna do this because I'm gonna show you, it's gonna allow us to do a decomposition. To convert this into into pollution concentrations, before we ran this like pollution dispersal model, here, we're just gonna take the IMAP source receptor matrix. Okay, what is this? For pollutant P, it tells me, right, how much pollution from facility I ends up in census tract or location J, right? So it's, you can think of it as like you know, a matrix where on you know, one dimension is like all the polluters, right? And on the other dimension is all the locations. And it just basically linearizes like, you know, like for one pulse of emissions from somewhere in Davis, how the rest of California is affected by it. Okay. So I'm just gonna, that's the beauty of this. This is now linearized. Okay. This is just a bunch of sums. I'm gonna sum to get average contributions to any given census tract. I'm gonna just basically sum over all facilities, right, of this product, and sum over all primary pollutants. Okay, so I'm gonna give you like secondary to them. To get at pollutant concentrations for the average person in a particular group, like the average white American, the average Hispanic American, the average Black American, I'm gonna weight each census tract pollution concentration by the population share of that group. Okay, so that gives me, this is just like, you know, this is population shares are coming in from census data. And then I'm going to just then look at disparities, which is like the gap in pollution across the groups. Okay, so that's all we're doing in a nutshell. Here's what this generates. So this is the CIP. So for a given year, this is pollution distribution from electricity for that census tract. This is for the most recent year in our sample, which is 2017. I thought this was pretty cool because I had never seen a map like this. But this is where, this is PM2, this is secondary PM2.5 from all fossil electricity generators in 2017. Okay, this is not ambient. This is going back to the source. Okay, and the black dots is where all the EGUs are. Okay, so you can actually, it's actually really interesting. It's not like spatially like distributed, like evenly distributed. Like we are, it's like we actually have like not much like electricity pollution in California. Why? Just because we have a lot of like, well, renewables, but also natural gas, right? Where places that have coal are places that light up here, okay? Like parts of Texas, parts of the Midwest, okay, parts of the Northeast, okay? So basically, we're going to take this and we're just going to overlay demographics onto this and ask what happens, and then also look at this over time. Okay, so just the cross section. What's interesting here is that there's a quite a pronounced gap when you overlay demographics. This is this amazing map that Don and A produced, which is showing this is just like minority share, so all the minority groups, and you can see that overlaid onto that previous map. Okay, and you can see that basically like places like, you know, with larger minority groups, so this is different, right? So like in the Southeast is primarily African Americans, in the Southwest is primarily Hispanics, okay? Overlay that onto the distribution from pollution. And you can see that there's a gap, like there's a very like pronounced, well, actually interesting, there's a gap, like Black Americans on average are experiencing more pollution than white Americans, but white Americans are actually experiencing more pollution from electricity, not overall, from electricity than Hispanic Americans. And the reason why actually is just, it's pretty obvious from the map is that more Hispanic Americans are living in the Southeast and the West, where it's just cleaner from electricity. Now this is not true in terms of ambient, right? Like if you look at California, there are more Hispanic Americans living in the Central Valley. The Central Valley is dirtier, but that's because of ag. This is just a map from electricity. Okay. All right. Interestingly enough, there's not a very strong income gradient. And it's largely because that there are rich and poor people kind of like everywhere in the US. Now, there's some spatial distribution, but like it's the US, this was news to me, it's much more, maybe not news to you guys, but it's much more racially segregated across space than income, by income. So like it kind of makes sense that like so much of our like language about inequality is about race and not about income, whereas in other places it's more about income. This is just like a factor of demographic patterns. Okay, I don't have much more time. Let me just show you the few headline results here. Let's just look for the average American. The black line is the change in pollution concentration, particulate pollution concentrations for the average American from electricity. The combination of all these forces, switching from coal to natural gas, cleanup of cleanup of electricity, has led to a almost 90% decline in pollution from electricity for the average American. Okay, so this is like a big, in my mind, like this is a very big deal. Interestingly, if you were to plot the change in ambient, so this is like everything, right? Everything, like basically the air that we breathe in, but that's like a consequence of all kinds of activities, polluting activities in the US, as well as that is transported from elsewhere in the world. This drop in electricity, pollution from electricity, is twice the rate of the drop in ambient. So electricity is cleaning up much faster than other sources of pollution in the US. Okay? The other thing that's like striking is that as a consequence of this, the gap across racial groups have contracted dramatically by about 95%. So now, throughout our sample, the average Black American is breathing in dirtier air than the average white American, which is breathing in dirtier air than the average Hispanic American. But look at the size of that spread in the beginning of our sample, and basically the size of that spread now. It's contracting about 95%. Okay, I'm gonna show you something at the end that like gives you pause for like not to celebrate this too much, but at least in terms of pollution concentrations, this is from electricity. This is what we're seeing. Okay, and I think it's largely, if you think about it, it has to do with this pattern. Like, where's the cleanup happening? Where's coal being phased out? In part by getting cleaned up in the southeast, right, and in the south, where more African American communities are located. Okay, all right. We don't see much of a gap by income, nor differences in the trends. We can do a decomposition, so so we can think about it like in terms of these terms, like each of these forces, like emissions intensity, share, and output. Okay, we do a decomposition. This term is ugly, but basically we do a decomposition. It takes that basically like that sum, that all those like linear combinations, and basically like vary one at a time. And basically what we find, and we just focus on the black-white gap, is that the overall scale of the electricity sector, like over kilowatt hour generated, play very little role. About 40% of it is due to the cleanup, like coal getting cleaner, and about 60% of it is due to fuel switching. Okay. We also allowed for basically like fixed where people live in 2000 and not move that. So we can think about the role played by like sorting or residential location, and that plays a very small role. Okay. All right. So just in summary, it looks like, I won't talk about, well, in California, in the first paper, we showed that emissions have dropped pretty dramatically, as well as the disparity. And for electricity overall in the US, the pollution disparity across racial and ethnic groups have fallen. Now here's the caveat. So you're like, okay, that's great. Like, racial disparities in pollution, at least from electricity, has fallen. Okay, or at least like, due to the policies, they have fallen. But we don't actually, at the end of the day, care about like pollution disparities, right? Really, we care about like health disparities. Okay, and so recent work that Don and I have been doing is to ask like, do these contractions in racial disparities translate disparities in air pollution translate to narrowing disparities in health outcomes? Okay, because at the end of the day, that's what we care about. And so here is like, literally this was like produced last week, where in California, now we're focusing on California, California, the average PM exploded by the average Californian has, this is for the US overall, has also fallen for California. Okay? So you're like wondering like, are the stories that we've learned in previous studies, do they translate? So we have data on the universe of all emergency department visits in California. So this is like administrative data that the state of California has given us access to, and we know who is going to the ER rooms across the state, why they're going into the ER, and what racial ethnic group they come from. In California, we see a fall elsewhere, focus on the orange line, in the disparity between Black and white Californians in terms of air quality, just as we saw in the other settings. But this is a disparity in asthma rates over the same period from this emergency room. If disparities in air pollution translate to lowering disparities in health outcomes, you should see this line fall. And if anything, what we're seeing is that this line is rising. So this is like the puzzle that we're working on right now. It's like, how is it that even though pollution disparities have been narrowing in California between Black and white Californians, the health disparities are actually worsening. Okay, and so what we're trying to get at in this data is some combination of like, it's not just about the air you're breathing in, but also your access to healthcare. Okay, and are there countervailing trends, unfortunate countervailing trends that are occurring in terms of health aspects of healthcare? They are basically not allowing, right, this to translate into health disparities. So this is something we're very actively working on right now. This is the last thing I'll show you. Yeah.
Yeah, that's great. Quickly, so for the PM2.5, is this with respect to electricity generation or kind of sampled PM2.5 from like EPA centers across the state? Because
this is from this product by Duncan et al., which is it's like a reanalysis of a combination of monitor data, remotely sensed optical depth data, and self-reported data, citizen science data. And it creates a spatially contiguous field at I think 1 kilometer by 1 kilometer level of like imputed surface PM concentrations.
Okay. I was wondering, especially like with respect to agriculture and racial disparities and those participating in agriculture, I was wondering if it was kind of using that same mentality of just electricity generated PM versus that. But that answers my question. So.
This is ambient. So,
Gotcha.
So let me just close here. So, this is like ongoing work. I think broadly we're trying to think about, as our economy is decarbonized, what happens to various measures of disparities. I should focus a lot on air quality disparities, but obviously the things we care about even from air quality is health disparities, but we also have been doing work thinking about like labor market disparities and so forth. This is like very early stages, I would say, of this work. And at least for me, the way I often think about this is like, we have all these policies, we have all these environmental policies. It is not obvious to me that like our standard toolkit of environmental policy, which is like cleaning up a place, necessarily narrows disparities. And so oftentimes in many of these settings, I think we need to think jointly about a combination of environmental policies that could clean up a place, but then also kind of more like EJ distributional specific policies to put on safeguards to make sure that as you clean up a place, that those benefits are being borne, by disadvantaged communities. It's not always going to be the case. And so a lot of this work we can try to understand that. I'll stop there.
All right, we are at our close right now. We do have like 2 minutes. If there are any more questions, stop them now.
Hi, thank you. That was a fantastic presentation. I have a question, maybe tangential, but back in the beginning when you were talking about the decoupling of the economy and emissions, I'm kind of interested. I'm wondering if you think that's a result mainly of the intentional decarbonization policies and efforts, or would you say it's been mainly driven by like the outsourcing of manufacturing and moving towards more of a knowledge-based creative economy?
Good questions. I would say, and I don't know if everyone others will agree with me, is that I would say we don't know. Like, Like, this happened really without like nationwide climate legislation. We had like patchworks of things that, we had some subsidies that were recently extended. We had some like renewable subsidies that, came under the Obama stimulus package. The Obama administration tried to have climate legislation that didn't pass. The fact that so here's another interesting tidbit. I asked my students a lot of this as well. Since 2000, what was the US's rate of decline in greenhouse gas emissions compared to California's? I think most people would be like, California's has been more, but actually they're about the same. And this was comparing, obviously the US includes California, but this is comparing a state that had all of these climate policies and the rest of the country that kind of was just like, I don't know, foaming it in, but somehow managed to do this. From one standpoint, you're like, phew, thank goodness. But why this happened, I actually think it's like how much of it, for example, was the expansion of renewables versus like natural gas? I actually think it's both, because look at what happened in September with this like peak demand moment, right? Like we had all these renewables, but we didn't have it when we needed it most at 5 and 6 p.m. What kicked in? Natural gas. Would that have been as readily available if it weren't so cheap in relative historical terms? Maybe not. And so how much of the fact that like across the US, the fact that we're able to facilitate renewables comes from the fact that we have very flexible generation, fossil generation coming in from natural gas filters, right? If we only had like coal, we probably could not have as much renewables because coal has very much higher ramp-up costs, right? So there's all these things that are actually like, I actually don't know, but these are the fun questions.
Actually, my question is about this same figure. So you mentioned that the gradual decline is taking place due to fuel switching.
Yeah.
But what was the reason behind the sharp decline in like 2009, 2012?
Oh, this is a recession.
Oh, okay.
This is a recession.
Because we don't see that in California.
Yeah, you kind of see it. California weathered it a little better. But this is where like making like causal claims is very hard. Because this, if I were to plot natural gas prices, that was also when fracking was introduced. So like right when the recession occurred was also when fracking became widespread. So it's hard to make causal claims because like at least in the aggregate time series, they're very confounded.
Thank you.